then send me the host.
Yep.
So sorry, Elena.
No, it's okay. It happens. I mean, it's not as cool if nothing goes wrong.
Well, we have a backup in these cases, but it seems the backup is not working either, so it must be a deeper problem.
It's okay. So
Okay.
maybe I should, since we started recording now, I'll maybe say again what we're going to do today, which we're going to talk about the physics of the physics that we can do in a liquid argon TPC, and we're going to touch on kind of three big categories. One is measuring properties of charged particles in test beam experiments. The other is measuring neutrino properties on neutrino beams, and the third is doing a non-accelerator physics with big, massive liquid argon time projection chambers. And they feed one into the others, this topic, in terms of both technology and physics that we want to talk about. So you need to measure the properties of charged particles that are relevant for neutrino interaction, so the products of the neutrino interaction, because if you want to study nuclear, they are interesting on their own if you want to study nuclear physics, but also in terms of what their importance, they're fundamental to understand the neutrino nucleus interaction, because again, like neutrinos are neutral, you can't really see them. So everything that like everything that you want to study on their interaction properties needs to stem from the charged particles that you get on the outside of your neutrino interaction. When we're going to talk, the first topic actually we're going to talk about is neutrino properties on neutrino beams, which is one of the big things that we're doing at Fermilab. And in this case, we're going to talk about measuring interaction rates in the context of cross-section and oscillation physics. I will tell you this many, many times. When you have a neutrino experiment on a neutrino beam, what your detector is actually measuring is the number of neutrino interactions in reconstructed energy. And I'm going to repeat this several times. But some of the physics that you care about, for example, physics, oscillation physics, actually hinges on or like the important parameters are true energy, for example. So when you're doing neutrino cross-section, you're again improving your understanding of the neutrino nucleus interaction, and you're doing standard model and beyond. And when you're doing oscillation, you're doing beyond standard model physics. Actually, oscillations, we always say that neutrino oscillations are the first lab-based evidence of physics beyond the standard model. In particular, if you're doing some CP violation, like in order to do CP violation and CP violation searches and long baseline searches, you need to build these massive detectors underground. And what we're trying to build at Fermilab, well, it's not at Fermilab, but under the Fermilab umbrella, is Dune, and there's a lot of other physics that you can do with Dune when you're not sending neutrinos to Dune, and you basically leverage the mass itself, the fact that you need to do like this 10 kilotons of material to perform exotic searches of, for example, grand unified theories. So again, like the idea is to use these detectors to do beyond standard model physics, solar and supernova neutrino physics. So let's talk about Fermilab though, like and again, like the title was LArTPC is at Fermilab. So Fermilab, actually the official name is the Fermi National Accelerator Laboratory, and accelerator is even in the title of the lab, which I think it's really tells you that the core of Fermilab is its accelerator complex. So in order to create neutrino beams, but also in order to create your charged particles that you're going to study in test beam experiments, you start with protons. And what you're seeing here is a picture of the accelerator complex. And basically, the final product is a bunch of very, very fast protons. And you do a bunch of things with them. Well, mostly you smash them onto something in order to create the beams of particles that you're going to study. But you start with gaseous hydrogen, which is ionized to be negative, actually, in order to create your protons, and you create your fast protons. And you accelerate it with I never get this word, a Cockcroft-Walton accelerator, and you accelerate them in stages. So you start with this first stage and you go from thermal to, so zero, no, it's not, they're not zero because they're not frozen, but you go from thermal energies to 750 keV. In your ion source here, you strip them of 2 electrons so that your hydrogen minus becomes protons. And then you start with other accelerator stages. The first one is the LINAC, which means that these protons are accelerated by radio frequency cavities, which in a linear fashion. And then there's several stages of acceleration in synchrotrons. The first one is the booster, that accelerates your protons up to 8 GeV, and then some of them get extracted and they actually go to the booster neutrino beam, the BMB, and they go and collide on the BMB target, which is beryllium, I believe. And some other go to the main injector, which is a bigger ring that allows you to accelerate these protons even more to 120 GeV. Once you have your protons that are running in the main injector, you can extract them again and you send them to some of the neutrino experiments, and you also send them to the test beam experiments, some of your fixed target experiments. So in real life, this is what the Fermilab site looks like. This is where my office was, or is technically. So this is Wilson Hall, the biggest, one of the biggest buildings around. This is the main injector. And what you're seeing here is what's left of the Tevatron, which was a collider experiment that ran until, I think, 2011. The test beam experiments are down here. So when your beam is extracted from the main injector, it goes into this line. When it's extracted for your neutrino experiments, actually goes to the neutrino campus that, like it's in this direction. Currently, the lab is busy in upgrading its proton, so it's doing a proton improvement plan, which means upgrading the accelerator complex in order to host the beam for Dune. Dune is going to be this, one of the biggest, it's the biggest LArTPCs ever built. It's going to be the largest TPCs ever built. And it's the flagship program of what we're doing at Fermilab, and it's going to have one of the most powerful neutrino, the most powerful neutrino beam ever built, which is what we're going to do at Fermilab. So in the neutrino campus, if we were to follow this line and look on top, at Fermilab, we would have 2 neutrino beams, the BMB that come from the booster, and the NUMI beam. And you can, for the nature of neutrinos, you can put several experiments, several different experiments in the same on the same neutrino beam, because basically neutrinos don't see anything. They just go through, and the fact that you're putting one experiment or 10 or even thousands, the neutrinos don't really care. So you basically get the same neutrinos, per the beam opening, per the geometry, let's say, in every point. Okay, so how do you make a neutrino beam, or how do you make a neutrino experiment? As I was telling you, you start with your protons. So you start with your accelerator complex, and you smash them on a target. This interaction will produce a number of particles. excuse me. And you care only about some of them. And you, like in particular, you care only about kaons and pions. So what you do after you have smashed your protons, you focus some of your charged particles in a straight, like towards a straight line, and you defocus the particles that you don't care about. So your K plus and pi plus will give you neutrinos, and when they decay, and K minus pi minus is gonna give you antineutrinos. And so if you only care about the neutrinos and you care about one type of particle at a time, you focus your horn so that you only get, or that you select only your K plus and your pi plus. So once you focus your particles, you let the kaon and the pion decay in what is called the decay pipe. Usually decay pipes are evacuated, so you try to put a vacuum in these pipes, because if you have particles, you want to minimize the kaon and the pion ray interaction in your beamline, because every time, because we're gonna see that it is important for you to know. The only way that you know how many neutrinos you're shooting is by knowing how many pions and kaons you had at the beginning. And so the fact that they interact, it messes with your neutrino count. After decay pipe, you have usually an absorber, which means that all charged particles that didn't decay and that were still focused, you basically have removed, and the only thing that it's left, it's your neutrino beam. And on your neutrino beam, you put your neutrino detector. So you put your massive liquid argon time projection chamber. In general, again, to do your neutrino experiment on a beam, you need a very intense flux so that you have a lot of neutrinos. And this is because your neutrinos don't interact very much. So you need to produce a massive amount. Usually when we talk about, we usually talk about proton on target when we talk about how many neutrinos or how big the flux is. And usually you shoot 10 to the 20, 10 to the 21 proton on target in order to have thousands of neutrino interactions in your detector. This is roughly like the proportions, the numbers we're talking about. So in your neutrino experiment, you would want to know the neutrino energy very well. Because the physics your physics question depend on the energy of the neutrinos that you're producing. We were looking at so if you start with 8 GeV protons, you're looking at 0.8 or 1 GeV peak neutrinos. You need to decide the oscillation baseline. So the oscillation we're going to see depends on the distance between production and when you start when you detect them. So that parameter is combined with the energy is what drives your oscillation surge. So depending on the physics that you want to look at, you need to decide where to put your detector. You need to decide when the neutrinos are turned on. So basically you have a trigger that tells you when the protons are coming. You calculate how much time it takes to get to your detector, and you only read out your detector when neutrinos might be present. And usually you do more than one detector on the same beam, because we're going to see it's good to measure them at different baselines. So
Elena, we have a question.
Yeah.
How do you absorb?
Yeah, I saw it.
Okay.
So how do you absorb the muons? So that's a good question. So the absorber is usually pretty massive, which means that even muons are slowed down. And usually we don't put the first neutrino, we don't put the first neutrino detector before about 100 meters of dirt, which it's usually enough to get rid of the muons. There are other things that are a little bit more challenging are neutrons, for example. They can wander quite long, and so if you can't get rid of them, you try to simulate them in your detector. Okay, so I hope this answers the question.
So basically 100 meters of dirt.
Yeah, 100 meters of dirt.
Okay.
What are the properties that you can measure with your neutrino beams, and what are the what are the programs that we use to do them? So the first program is the short baseline neutrino program. This comprises 3 detectors on the beam. It's weird, in most of these pictures, the beam goes from right to left. This program is a multi-detector program. It's based on 3 liquid argon time projection chambers. We have the short baseline near detector, which is this guy here, and it's about 100 meters of dirt from the point of production. And then we have the microboom detector at 470 meters. This is an 85-ton detector, and then we have a 600-ton detector, which is Icarus. 470-ton detector Icarus that is at 600 meters from the point of production. So again, like the idea of this lecture is giving you a taste, and there's going to be some simplifications that I'm going to do when talking about the physics that we're doing. And so throughout the talks, you're going to find again archive links, mostly archive links that should lead you to the actual measurements and the actual, like the proper literature if you're curious about this. The type of physics that we're doing in these detectors are neutrino cross-section on argon and short baseline oscillation and stereo neutrino. And we're going to talk about both a little bit more. So in terms of where we are with the program, the near detector is under construction, and it's expected to be taking data in about 2 years. Microboom has been operational since 2015, and it's winding up its run, its physics runs, and winding down its physics runs. And Icarus just started, like it started, I think, earlier this year. And I showed you a bunch of pictures from, like, this is a bunch of data from Microboom, and they started seeing neutrinos in Icarus as well. Okay, so the other, as I was anticipating, your other big program is Dune. It's an international flagship program, and it's going to be massive, mostly massive. So we're going to shoot neutrinos from Fermilab. Again, we go right to left, and these neutrinos are going to travel 1,300 kilometers underground, and they're going to be collected, or some of them are going to interact in 4 10-kiloton liquid argon time projection chambers, which will be underground. I should have said that the SBN program is above ground, so it's surface TPCs. We're not going to dive into that, but it means that you have different backgrounds compared to when you're underground. The big physics ticket of Dune is exploring CP violation in the neutrino sector, doing a precision measurement of the neutrino mixing parameters, especially in, of course, long baseline oscillation. Again, like the baseline is how far the neutrino travel, and figure out the neutrino mass hierarchy. All of these guys are correlated, are oscillation measurements, but also, and the things that we're actually going to talk about a little bit more is beyond standard model processes, for example, proton decay and bar oscillation, and there's the hope to see to be online while supernova goes off in our galaxy, and it would be in our local group, and it would be really cool to see neutrinos from there with Dune. Again, this is another resource. It's a little old, it's about 10 years old, but it's a great, in my mind, it's a great resource for understanding the physics of Dune. Okay, so in terms of where we are, with Dune, the mine underground in South Dakota is the same Homestake mine, which hosted the Ray Davis historical experiment. This was the first evidence of it's what started the neutrino solar problem, and so the first evidence, like looking back of neutrino oscillation, but which really started this great exploration of neutrinos. So for the fire detector, the excavation started there are demonstrators in place, both either taking data or already built, for both the near and far detector. And what you're seeing here on the right is a picture of inside ProtoDune, which has just ProtoDune has just completed their first physics run. And again, gives you an idea of how big these detectors are. And in terms of ProtoDune, what they also did was to test components that that are going to go in Dune, in a one-to-one scale. So the real, the real APAs, the anode plane assemblies, and they're really testing the engineering solution for this gigantic detector that's going to be Dune. Okay, let's talk with, so if there are any questions here, I want to talk about how to do a cross-section, a neutrino cross-section in microBoolean or SBND, or in the SBN program, which is one of the things that we're supposed to do while we are constructing Dune. I'm just gonna wait 1 second, and then I'm gonna go. We can ask also questions at the end. Okay, so let's talk about cross sections. So first of all, what is a neutrino cross section and how you measure it? So neutrino cross section measure the probability for a neutrino of a certain flavor to interact with a target nucleus in a certain way. This is very vague, but I wanted to keep this as vague as possible because the recipe for doing cross section, at least in the most generic way possible, it's pretty standard. Now, there are complications when you're doing the measurement itself, because every piece that you're trying to measure, it's its own little beast. But in general, yeah, you're basically counting the interaction of a certain type. You know how many neutrinos were sent to you, and you find the probability that they interact. So you can do single beam or differential measurements, and I can briefly talk about that. But in general, the simplest formula for a cross-section that you can think about is the one that you're seeing right now. So sigma is your cross-section. This is single beam. And N is the number of selected events. So the number of events that you pick, of neutrino events that you were able to pick out in your event, following some criteria that you applied to your data in order to figure out if you had an interaction in your detector. So, for example, if you want to measure electron-neutrino interactions, the electron-neutrino charge current interactions, so those interactions where you had an electron-neutrino that came into your detector and actually interacted with your argon, you might want to select events that, for example, only have an electron shower. So events that that your TPC recorded while Fermilab was sending you beam, and that had a reconstructed shower consistent with an electron as part of the topology. And Wednesday, we talked at length about reconstruction and how kind of difficult it is to pick out, to understand what's going on in an event if it's quite complex. So you need to write algorithms, for example, that pick out that ID, that identify protons and identify electrons. And so these selection of event can be quite complex. The other ingredient that goes into this is that your selection is not only going to pick out your signal. So if you're interested in looking NUEs, it's possible that you're gonna pick out something that is not NUEs. And so in order to understand how the probability of your NUE to interact, you need to remove those events. And so B in this case is the number of expected background events. And this is not something that is something that you estimate through a simulation. The next number that is important is the efficiency of your selection. So again, your selection is not perfect and it's not going to pick out or select every NUE interaction that that you had in your detector. And so you need an estimate of how well you are selecting your signal, your neutrino event. The next number that is important is the flux. So of course, if I had sent you 3 neutrinos and you pick out 1, that's a different probability that if I had sent you 1,000 neutrino and you picked 1. So this portion here takes care of how many neutrinos you're getting in your detector. Not necessarily how many they interacted, but it's basically, I mean, it's your denominator in a probability calculation. And then, of course, if you have a lot of targets, you're like that is also like how big your detector is gets into the number of targets that your neutrinos are seeing. In terms of the flux, we were talking about a second ago. You need to have a really good prediction in order to calculate to measure your cross section with not a gigantic uncertainty. And for example, this is the neutrino flux as a function of the true neutrino energy, and it's divided by neutrino flavors. So you see that this is a log scale, but most of the neutrinos that we are getting in microboon and in general, most of the neutrinos that our beam produces are nu mu's. There's a little bit of an anti-nu mu component because when we're focusing those pions and those kaons, the focus is not perfect, and portion of the decays is actually anti-nu mu's. And then there is a little bit of a NUE and anti-NUE component. Now, this component, especially in the BMB, so in the booster neutrino, we really would like this to be very suppressed. In order to do oscillation analysis, which is something that we're going to talk about in a second. But there is a little bit of a component. And again, like understanding how well you know your uncertainty on the flux prediction are usually constrained with data that is called with hadron production data, which basically is like separate experiments that were actually done quite in the past, where that studied the pions and kaon interactions in the materials that you construct your neutrino, like in the beryllium or in the materials that you construct your neutrino beam with. Because again, if your kaons and pions get eaten in some sense, they are not going to decay, and so they're not going to give you your neutrinos. Okay. So yeah, when we were talking about developing a selection and this idea of background versus signal, if you're doing a NUE search, you actually want to pick out events like this, but writing an algorithm that picks out events like this versus events like this, which is your background, might be kind of challenging. And so again, like you really need a very good simulation of both your detector and how well you know your selection, but also of the nuclear model in some sense, or how like your neutrinos are looking in your detector in order to write the algorithms that pick out this type of events. And given the important role of these interactions and understanding the nuclear models, again, like if neutrinos don't interact, you cannot see them. The SBM program is doing big campaigns for measuring the cross-section for measuring cross-sections. What I'm showing you here, and there's the archive link to 2 of the many cross-sections we've been doing in Microboon, are a NUI single beam cross-section actually performed on the second beam, on the NUMI beam, which we see we're exposed to this in Microboon. And then this is the first cross-section we've ever measured in Microboon, which is a new mu differential, double differential in lepton, angle, and momentum. So your cross-section, so your probability of, you can measure probability of interacting just, like you can ask different questions. That's what I'm trying to say. You can ask how many new mu's are interacting, or you can also ask how many new mu's of this particular momentum are interacting in my detector. And doing the double differential cross-section means also knowing very well and measuring very well, for example, the momentum of the muon or the angle compared to where the neutrino beam is going. And different, doing, these are called, so doing differential cross-section or exclusive channels, one question that you can ask is how many interact, like what is the probability that my NUI gives me 3 protons? That's an exclusive cross-section. Like diving into this really gives you a measurement of the neutrino nucleus interaction, and you can learn things about you can learn things about the nucleus, which is the big physics ticket when you're doing cross-section, but you can also improve your modeling of your neutrino interaction in order to do, that is a major systematics when you're doing oscillation measurements. And I'm gonna touch on oscillation measurement in a second, but I can stop if you guys have questions on cross-section, on neutrino cross-sections.
So I have a question. What's the dominant systematic in the measurement?
It depends. So in these particular ones, in the NUMI one is the major systematic is the NUMI neutrino flux, because Microboon is very off axis from the NUMI beam. And so even if the measurement here is statistically limited, the biggest systematic is how well we know the NUIs and anti-NUIs actually that get to the detector. And for the double differential, I am not sure. It's been a while since I read this paper. I didn't do the measurement, but I did this one. So, or I mean, it's within my group, and so I can get back to you. But usually, I mean, the flux is a big one.
And another thing that wasn't, maybe you said it, I didn't get it clear, is the cross-section, of course, goes as 1 over E, right? E times the Now, you have a mixture of energies here. So basically, you are measuring the cross-section for your mixture, right, in each experiment.
Yeah. So, yeah. Well, yeah. So that's an extremely good point. So when you're doing a single bin like this, if you want to compare these numbers to somebody else that is maybe in a different beam or in a different, or maybe still argon, but on a different beam. And we actually did this for, there's another measurement from Argonute, which is the same nucleus, but it's on a different portion of the NUMI beam actually. You can't do it like willy-nilly, like you can't just take the 2 numbers and put them together and see if the error bars are lying. The thing that you actually need to do is to have the flux. So you need to have the flux prediction in order to understand So in order to understand if your measurements are compatible, because it's exactly what you're saying. Like it depends on how many neutrinos of a given energy you are expecting at your detector. So yeah, it's an average in terms of the energy, and it's also not just a simple average. It depends on the shape of the flux.
Okay. Someone else, any question? I think we're good to go.
Okay, so we're going to talk briefly about oscillations, and I stole this really fun picture, in my opinion, from Silvia Pascoli, that represents neutrinos as chameleons. So one of the biggest, like one Nobel Prize winning discoveries been neutrino oscillation, and in a nutshell, what happens is that you start with neutrinos. You produce neutrinos of a certain type. These neutrinos propagate, and then when you detect your neutrinos, a portion of them have changed flavor. And there's kind of these three. I like that there are these three very distinct stages of neutrino oscillation, because it's really like it maps really well in my mind into quantum mechanics and like your observation of a certain phenomenon. So when you start producing neutrinos, you in a beam, your neutrinos come from the decay of pion and kaons. So their flavor is locked in. Like you need to conserve flavor, and so when your pions and kaon decay in neutrinos that are of a given flavor, then when these neutrinos start propagating, you do like your propagation is a quantum mechanic propagation through basically this formula here, and they propagate through their mass state. So in this equation here, it's hidden in here is the mass of your neutrinos. And so the fact that, well, we always say that neutrinos are the first evidence of physics beyond the standard model, because in the standard model neutrinos didn't really have a mass, so they were massless. And so when you see if the oscillations are real, and we have overwhelming evidence of that they are, then neutrinos have masses because they propagate through massive states. So neutrinos 1, 2, and 3. And when you detect them, though, like you're opening the box of your cut Schrödinger box, and you're observing only if they interact, and they interact exchanging a W boson if they're doing CC interaction. And so again, you're measuring the flavor of the neutrino state. And so in order to understand, like the oscillation parameters are the oscillation state are governed by the PMNS matrix, which is at least a version of this is here. So that go from your mass eigenstate to your flavor eigenstate. And if we simplify this and calculate the probability only for two flavors, this is what you get. So you have your neutrino of a certain flavor, and you're trying to calculate the probability that after a certain point after that it travels a certain length, you actually have it has transformed in neutrinos of a different flavor. And you calculate this probability using the PMNS matrix, and the parameters that you care about. Oops, I forgot about something. The parameters that you care about are the energy of your neutrinos and the baseline, so the length of your between the point of the length between the point of production to the point of detection. So if we were to expand the PNMS matrix, all this, and it's going to be very brief because I'm a terrible theorist, I'm not a theorist at all. So you can parameterize this with oscillation mixing parameters, and especially the angle 2, 3, 1, 1, 1, 3, and 2, 1, and 1, 2. And your CP violation phase, which is something that that we are going to be doomed to explore. Okay, so depending these parameters that are hidden in this matrix, the way that you measure these parameters again, like depend on this L over E parameter. And so different baseline and different energy of your neutrino beam probe different parameters of the matrix. So in a very in a not too correct way of thinking about this, you can think about the probability of oscillation in two flavors, and each pair of them probes a different parameter. Now, when we're talking about oscillation at the short baseline, we're not really talking about this particular matrix, but we're talking about a slightly modified one. Meaning, when we are searching for sterile neutrinos, we're actually searching for a fourth neutrino. So, and when we're talking about sterile neutrinos, we're thinking about neutrinos that don't produce, like that don't interact with like your matter, in the same way that nu e, nu mu, and nu tau interact with matter. So I butchered the matrix here, and I am adding a fourth state means that you also change the shape of your oscillation matrix. But your oscillation matrix, your matrix still needs, the probability still needs to sum to 1, which means that if you started with a certain amount of neutrinos at the beginning, you're going to have the same amount of neutrinos at the end. So if you're predicting a certain amount of nu e's at a certain baseline, and you find more or less, or actually more of your nu e's, then what could have happened is that your assessment of the probability was not correct because you were not accounting for a fourth state. So in other words, if you have a fourth state, the probability of your probability measurements at a certain length for a given energy of neutrinos change. And this is basically what, this is one of the possible interpretations of what it's called the Mini-Boon low energy access. So there was an experiment at Fermilab called Mini-Boon several years ago that is in the same booster neutrino beam baseline, and is actually very close to where microboon is. And what they saw was that when they were looking at when they were picking out electromagnetic, neutrino events that had electromagnetic showers in them, their data was pretty much above their Monte Carlo, their simulated prediction. And so the main search at the SBM program, which is on a very similar baseline as Mini-Boon, is to understand what happened here. So if we actually have a fourth neutrino, which changes again this probability of interaction. I should say that, you know, like this, that Mini-Boon was a Cherenkov detector. And so compared to the LArTPC, they weren't really able to distinguish between electrons and photons, and electrons and photons. And so the strength of doing a similar search with more detectors is to basically change the backgrounds that you have in picking out your neutrino interactions. And there's one more advantage is that we have more than one detector. So talking again about the SBM program, we were I told you at the beginning that the first, that we have one detector online, which is, that has been taking data for a while, sorry, which is the microboon detector. And this is the closest to miniboon. So in microboon, we're gonna try to see if we have a similar shape that miniboon saw in similar, with definitely looking for doing an electron search and a photon search. And by the way, the results are coming very soon. I cannot talk about them, because it's kind of the big result that we're hopefully going to publish before the end of the year. But it takes time. But the other big strength is that we're going to have, we're not going to have only one detector, but we're actually going to have a near detector and a far detector. And so when you're doing oscillation searches, and this in general, but especially in this is an advantage compared to the miniboon experiment, which was only one experiment. So if you're doing an oscillation search, you try to measure your beam of neutrino twice in the near detector here, which is as close as to the production point as you can, because you're trying to measure the non-oscillated, the unoscillated neutrino flux. So before these guys even propagate, you try to measure how many nu e's and nu mu's you had of a certain energy at the near site. And you're trying to constrain the neutrino interaction model. And then you measure them again after they have traveled the length of the baseline, and you measure the interaction again. And if you find any difference after you account for the fact that you have different acceptance in terms of the detector, then you can interpret this in the framework of neutrino oscillation. And this is especially important if you have the same same nucleus. So summing up, if there's one thing that you get away from this talk, is that your LArTPC measures neutrino interactions in reconstructed space. And there's a lot of other modeling that you need to do from getting this information, that is what the your LArTPC does, to the physics that you want to measure. So for cross sections, you need to know very well what you're shooting in your detector and how well you identify it. So backgrounds and efficiencies. Flux uncertainties can be constrained with external data, and it's your job to calibrate your detector very well. For oscillation, you need to do all of the above, but on top of them, you also need to know to know the cross section, because you really don't want to mistake a cross section effect for like an oscillation effect. So if you don't know very well how many neutrino were supposed to interact in your detector, it's hard to say, oh, well, they disappeared or they appeared because of oscillations. And then the other thing is that your nuclear model is what brings you from your neutrino products that you measure to your true neutrino energy. And your oscillation parameters depends on your true neutrino energy. Doing near-far ratio, so having more than one detector, especially of the same nuclear type, helps you a lot, because again, like, you can diminish the uncertainty that you have on the interaction model if you use the same argon, the same nucleus, for example, argon. Roughly your efficiency for picking out the interaction that you care about, for example, nu is the same. And I'm already telling you a lie, because of course it's the reality is a little bit more complex than that. You need when you're doing a multiple detector analysis, you need to basically calibrate one against the other. So nuclear model, like while in cross sections where you're trying to measure the nuclear part, your leading systematics is often the flux. Nuclear models for neutrino interactions are often the dominant systematics in oscillation, one of the dominant systematics in oscillation studies. Okay, so before I switch gear, any questions on this? If not, I'm happy to take them at the end, since there's still quite some ground. Okay, so we've talked about neutrinos quite a lot, and sending neutrinos, measuring the properties of neutrinos. And one of the things that, and the last line that we stopped, on which we stop here, is neutrino interaction model. So when you're creating your neutrino interaction model in neutrino generators, for example, Gini, Jibu, or Neuro, there's many neutrino generators. Neutrino generators are responsible for simulating what happens to neutrino interactions inside the nuclear matter. So when you're building this stuff, and when you're building your simulation of your detector, and usually this is done with GM4, which is the simulation package, most of what you're doing is simulating and building on the physics of charged particles in the nuclear medium, because again, like your neutrino interacts, and then it produces a bunch of charged particles, or neutral particles actually, and those can reinteract within the nucleus, and when they leave the nucleus, they can reinteract with the medium of your detector. And so it's important that we measure properties of charged particles, especially in a nucleus that is as heavy as argon. Argon is a pretty big boy. Okay, so in order to do so, Fermilab and CERN, with the partnership of Fermilab, has as test beam programs, and in particular, we put liquid argon time projection chambers on charged particles of beams of charged particle. You do this you do a lot of detector R&D in these test beam experiments, mostly because they're, well, not protodune, but you do a lot of demonstrators on these test beams, and LARIAT was one of them. LARIAT, as I was saying, was saying 2 days ago, it's a pretty small detector, like the order of meter. Protodune is gigantic. It's like 11 meters. It's a cube of 11 meters. And the type of physics that you do in these detectors are hadronic cross sections. So, so you are trying to characterize, again, what are the interactions, what is the probability of interactions of your protons, of your pions, of your kaons in liquid argon. And on top of that, you can also do, in some cases, for example, LARIAT, you can also do anti-proton annihilation. So you can study what antiprotons are doing in argon, and we're going to talk about them again towards the end of the talk. So first of all, they're really pretty, so they look like star. But anyway, so what I'm going to talk about is hadronic cross-section, and in particular, pion cross-sections, which is a really dear topic to my heart, because this was my thesis measurement. In LARIAT. So again, like these measurements feed into your neutrino experiment, because again, like neutrino modeling of your interactions in the argon is really a big part of the measurements that we just talked about, given a lot of the assumptions that you need to make. And we saw yesterday, or Wednesday, how the nucleus is a complex beast and there's a lot going on, and pions are actually one of the biggest products of the neutrino interactions. So studying pions by themselves is actually really important. And pions can do a lot of things in the nucleus, like the hadronic. So this is when we're doing hadronic cross sections, what we're studying is the strong force. And the strong force is super rich. It's fantastic. It's so difficult. I prefer to do neutrino physics. So a pion in liquid argon has many interaction channels, and I'm showing you here all the ones that, like all of them, and all the ones that we can study in LARIAT. You can have a hadronic elastic scattering where you have, I should say that in LARIAT and in protodune actually, you're shooting the charged particles, so you know what particles are coming in, and these event displays all show your pions traveling from left to right, as it should be. So your pions enter from here, and then this is the interaction location. And in this particular case, you have just a deflection, which is an elastic scattering. You can also have inelastic scattering, where your pion knocks off, for example, a proton, and then keeps going, and then the pion keeps going. You can have pion absorption with production of protons, which looks like this. There's a pion, and then 3 protons are coming out. And then you can have charge exchange, where you start with a pion of a certain charge, and you have production of pi naught and the exchange with the nucleus, basically. And then you have the ejection of the pion of the different type, of the different sign, and then production of pions, where a bunch of pions are produced. So you need to think about this as like, if you have these pions in a neutrino interaction, first of all, you have your nice vertex, and then there's a bunch of this stuff attached. Like you can think about this as attached to your neutrino vertex, or also you can think about these guys happening inside the nucleus as part of the final state interaction. So, so pions and the fact that they interact hadronically really contributes to the complexity of your neutrino event. So somebody 2 days ago was talking about, oh, well, there's 4 protons in this neutrino interaction. Well, yeah, I mean, it's possible that there was a pion in the nucleus, and then 3 protons came out because it was absorbed in the nucleus. So you see, like, your neutrino physics start becoming very complicated. So again, like, pions are important because they're a big portion of the of neutrino interaction, or the products of neutrino interaction, and also studying, and it's important to study them in the nucleus that you care about. So in particular in argon, because the shape of their cross section, so their probability of interaction, changes as a function of the nuclear medium. So for example, these are, you know, like you go from helium here to lead, and, you know, like the probability of interaction changes quite some. We don't have, before, you know, like before LARIAT, we didn't have any argon cross-section with pions. And similar arguments can be done from protons and kaons interaction in argon. We don't really know them. So, modeling packages use interpolations from data that is already present, so lighter and heavier nuclei. So we perform these measurements in dedicated test beams. And in a nutshell, a test beam experiment is an experiment where you have a baby version of your neutrino experiment. So for example, LArTPCs, but we also do it with other, we also put other mini neutrino experiments in charged particle beams. And then you shoot them non-charged particles. So you know the particle identity and the momentum before these particles even get to your detector. You determine, so I'm giving you here a picture of what a test beam experiment looks like. The top is actually an aerial view of the LARIAT beamline with the LARTPC here. And this is what actually kind of looks in real life. It's a different test beam, but it's as messy as the one that we had in LARIAT. The key components of the beam need to tell you the momentum of your particle that you shoot in, and the identity. And so in order to do this, you shoot, you know, like from going back to the accelerator complex, you shoot your 120 GeV proton on a target, and then you focus only pions in that case, and you make a secondary beam, and in your secondary beam you smash these pions again, to create a tertiary beam, which attenuates the protons quite some, like the number of particles quite some. And this tertiary beam you send down to your test beam experiment. And those are the ones that you characterize. The big element, the important elements for the reconstruction of the particles before they get to your LArTPCs are time of flights, which are these guys here. Wire chambers that you have 4 of them. You have one here, one here, one here, and one here, and 2 bending magnets. The wire chamber tell you where the particles were at this point in their flight. And basically the combination of their position in these 4 points in the beamline and how hard you drive the magnets gives you a measurement of your momentum. You basically, it's Lorentz force. So you know where the particles were before they got deflected, you know where the particles ended up after they were deflected, you know the strength of the magnetic field, and you know what is the momentum of your particle that gets into your TPC. In order to know the identity, you measure the time of flight. So you measure the time that it takes to go from the upstream time of flight to the downstream time of flight. And the information from the time of flight to combined with the momentum gives you the mass of the particle, so the identity of the particle through this equation. And if we're actually, like this is actually a plot from LARIAT, and if we are plotting the reconstructed momentum versus the time of flight, you see that you can distinguish different types of particles that are in the beam. So these are pion, muon, and electrons. These are kaons, and these are protons. So we can study, and this is deuteron. You know, like you can do cuts and select all events that of the particle species that you care about. And there's a 1 to 10% contamination depending on the particle that you care about in the identity of the particle that you're selecting. Okay, so now how do we perform a cross-section, a hadronic cross-section measurement in a beam like this? In 3 simple steps. The first is you select the right particle in the beamline. So if you care about the pions, you pick out the pions before they enter the TPC with your beamline detectors. Then you need to do a beamline to TPC handshake, meaning that you need to match the information that you have from the beamline to the TPC. And usually, you know, like you do some tracking matching, so you know the position of your particle at the downstream wire chambers, and then you have your beamline candidate in the TPC, and you match spatially the reconstructed track with what you had in the beamline. And this is really powerful because again, like you know in the TPC what was the energy of your particle when it started being in the TPC here. And you do so by the measurement that you did with your beamline detector, so the momentum here. You need to do a mass hypothesis because, and again, like you know the identity. Oh, this was supposed to be m, not m squared, I'm sorry. And there's some dead material that is not instrumented from where you measure the momentum to where you start tracking in the TPC, like your particles need to go through the cryostat wall, for example. And so you need to remove that bit in energy, but then you really know what is the energy at the beginning of your track. But also you're measuring, since the TPC, because you have a TPC, you're measuring the energy of your pion at each step. So this guy, as it slows down in the TPC. Actually, this is a kaon event, but okay. It slows down in the TPC, and your TPC is measuring at every bit how much energy deposited you have. So you actually know the energy at each single step. And this is important in order to measure the cross-section, as we're gonna see in a second. So step number 3 is applying the thin slice method, and it's a big one. This is actually a pretty big step, so it needs a slide. So so it, like the bread and butter of target experiment is thin target experiments. So at their bare bones, when you're measuring cross section on a thin target, what you're measuring is you're basically sending a bunch of particles on a thin target. You know how many you sent. You measure how many survived, and basically whatever the difference is how many interacted. So and in general, you can write the survival probability as this function here, where your survival probability is depends on the cross section or your hadronic cross section. It depends on how big the slice this slice here is, and it depends on the density of your target medium. And again, like you can write the survival probability as by a simple measurement of the number of particles that that interacted divided by the number of particles that were incident. Now, in thin targets, this slab of material is thin, which means, and it's thin compared to the probability of interaction, compared to the interaction length. Usually, that's the proper way of calling this variable. So, if this guy is small, you can do a Taylor expansion. So you can say, okay, well, the probability of interacting then becomes proportional to this, and your cross section, which is the number that you want to measure, this guy here, has a very simple relationship with the number of the numbers that your thin target experiment is actually measuring. That is your number of interacting particles over the number of incidents. So the number that you count at the end of the experiment and the number that you sent in. Now, like LARIAT, it was a small target, but it wasn't as that wasn't a thin target experiment. So the pion interaction length is about 50 centimeters, and LARIAT was 90 centimeters. But what we do is we don't think about LARIAT as one slice, but we think about the granularity of the measurement as a series of thin slabs. So basically, you have many thin slab experiment, one after the other, and you can recover this formula here if you're considering each slice separately. So each of the tracking point as a different target. So this is the method that we use. So for each of my beamline event, I slice my TPC in many points until I get to the interaction point. And so if nothing happens in the first slice, I'm gonna record its energy only as one of the incident cases. And then I keep going with this until, and in each slice, I keep filling this incident plot. And when I get to my interaction point, I'm gonna say, okay, I found an interaction, so I'm gonna count this as one of my interactions at the kinetic energy that I found that. Like, and remember, we know the kinetic energy because the beam tells us, and then the TPC is measuring each point. So you recover this nice and easy formula, and doing the ratio between this plot, you recover the cross section. Now, this is of course a lie, meaning that things are in real life are, you know, the TPC is measuring each point. So you recover this nice and easy formula, and doing the ratio between this plot, you recover the cross section. Now, this is of course a lie, meaning that things are in real life are, you know, the TPC is measuring each point. So are more complicated than this. The format that we actually use has a bunch of corrections because, again, like our reconstruction is not perfect. We have contaminants from the beamline, so things are a bit more complicated. But this is the method. Like you start with your pions, you find your interaction, you count how many interacted and how many didn't interact in the slice, you take the ratio, and you get the cross-section. Oh. So in summary, for the hadronic part, so in test beam experiments, we study how the product of the neutrinos behave in the same medium and with the same technology used for the neutrino experiments. But we have a big advantage because we know what we shoot. Like we're not tied to our nuclear model to know what comes out of the neutrino interaction. There's little to no data available for hadronic cross-section in argon, and so this is why we're doing this experiment to begin with, in order to minimize the uncertainties that are associated with the interaction model in argon. So more data in argon means better model, which means better characterization of your neutrino interactions, which means better neutrino cross-section, which means better oscillation measurements. Okay, so I have some other quick slides on the non-accelerator physics program at massive LArTPCs. And I don't know, should I can stop a little bit. Can I have like 5 minutes back?
Sure, absolutely. Yes.
Okay. Okay, so, but if you have questions, I mean, this was a lot. I tried to pack a lot of this measurement and I went into a little bit of details. So maybe there's clear parts that are not very clear about this. If you have questions, please tell me. Okay, I see something. Hold on. What kind of corrections you have to deal with within this thin slice method? This is a great question. So there's two main corrections. One is for muons. So I told you that we pick out, like we know the identity of the particles before they come in, and I lied to you a little bit. Meaning that we cannot distinguish very well between pions and muons with our current setup. Like protodion is going to do much better, I believe. At least in LARIAT, we couldn't, but protodion is going to do much better. And so basically muons, what muons do is that they basically traverse the TPC like it's nobody's business. And which means that none of the slices are interacting, and your cross section is actually gets a normalization, goes back down a little bit because you're counting way more in your denominator than what nature actually gave you. So this is one correction. The other is sometimes your reconstruction doesn't really stop at the point of the interaction. Sometimes it stops before, and sometimes it just, in a case like this, you really would like it to stop here, but it might pick up a little bit of this proton. And so you're missing some slices, or you're adding some of the slices. And again, we do Monte Carlo assessments to understand, to correct for this. So this was a great question. I spent a lot of time in the last year trying to get this right. Okay, there's another question. You're welcome. Okay, so let's talk about non-accelerator physics at massive liquid argon time projection chamber. So I did a kind of weird choice for this lecture. I completely skipped, or I just mentioned CP violation, neutrino mass hierarchy, and the measurement of the θ23 octant in Dune, even though mostly we're building Dune because of that. Like that's the biggest thing that we want to to measure in Dune. And I did this on purpose because the experimental challenges are pretty different, meaning, and the systematics are pretty different. Like technically, your massive detector has different problems than different challenges, not problems, the challenges with respect to the short baseline neutrino program, and your systematics, like again, like they need to be constrained more. So it's, there's some differences, but in terms of things to think about when you're thinking about oscillations, or you're building in your mind an understanding of oscillation experiments, philosophically speaking, it's fairly similar to the oscillation experiments that you can have. You just have a very long, very, very long baseline. It's not really true because you also need to care about of the mass effect, because of the fact that you have a lot of Earth in the middle actually messes with your the number of your neutrinos that you're getting at the fact detector. But again, philosophically they're similar, I would say. So we're going to run this detector for a very long time. And it's a fair question to ask what else we can see in Dune that is not neutrinos that we're shooting ourselves there. So this is a technical design of one of the modules of Dune, and this thing is really big. So it's going to be 18 meters by 19 meters by 66. And so and there's going to be 4 of them, even though technologies are not exactly the same for all of them. But this is there's 40 kilotons of argon that are going to sit in a mine for a very, very, very long time. So the other things that you can think about measuring are rare events and supernova neutrinos. So we're going to talk a little bit about rare events. So in particular, when we're talking about rare events, we're talking about searches for proton decay or bounded neutron decay and NN-bar oscillation. The signal that the signature that you're looking for, I should say, our Dune fire detector is going to be in a mine, which means that there's there's no cosmics, there are only atmospheric neutrinos and solar neutrinos. And it's going to be very quiet. There's no other activity in the detector but the neutrinos that we're sending, and eventually some non-beam physics that nature is going to send us. So the signal for a rare event like an NN-bar event. NN-bar is the spontaneous oscillation of a neutron in an anti-neutron. And if this happens, you are going to have an anti-neutron hanging out in your nucleus, and it's going to find a neutron to annihilate with. And the signature is this kind of star shape, like 2 GeV deposition, 2 GeV, because you have the energy of the NN bar. And it's going to give you a bunch of pions and some protons actually in the final state. And this is something I was telling you about before when I told you we can shoot antiprotons in the TPC with LARIAT, and we can see the topologies, and it's going to look kind of like this. And for proton decay, we're going to talk about the signature in a second. The other fun physics that we can do with Dune is waiting for supernova neutrinos. So in one Dune module, which is about 10 kiloton, we are expecting 900 events for a supernova that is 10 kiloparsec away. And the signal, it's going to be electrons in the MeV range with a big burst at the beginning and then a rise after some seconds. So this is so starting, hopefully Dune is going to be online when the next supernova burst will arrive, and the hope is to study the supernova time evolution in great detail. And just to give you an idea, we as humanity has detected supernova neutrino before in 1987. Like these events are quite rare, like they happen every 30 years or so. And all the information that we have and all the studies that came from supernova 87 were done with about in order of 10 events. So again, would be very exciting to have a new detector with a different technology. They were done by Super K, by the way, and another detector that is slipping my mind right now. So this, like if Dune is online when the next supernova event happens, it's going to be really cool. So we're going to go back to our rare searches event, and in particular for proton decay. Okay, so why should we look for proton decay? Isn't the proton stable? Yeah, I mean, it is, especially in the time scales that we usually look for protons. So the standard model conserves baryon number. What does this mean? It means that if you started in a system with 3 quarks, you can do a lot with it, but you still end up with 3 quarks at the end. You cannot end up with 2 or 4. But this conservation is somewhat accidental. So conserved quantities in the standard model, quantities in the standard models are conserved if there is an underlying symmetry according to Nader theorem. But there's not really a symmetry that concerns baryon number. There's nothing that tells you that this quantum number is actually conserved. So proton decay is a process that, or an oscillation is a process that violates baryon number, and is predicted by almost every grand unified theory. So what is a grand unified theory? So we can think about, maybe you've heard about the electromagnetic force. Well, sorry, I should say, when we start thinking about our theories and we think about electricity and magnetism, we had a unification, and we now call it an electromagnetic force. And so when we, in our normal everyday life, you kind of have 4 forces, which is electromagnetic, weak, strong, and gravitational. But if you look at interaction at higher energies, in this scale here, the electromagnetic force and the weak force actually become the same force, and you have electroweak force. And there's a grand unification theories that tell you that if you go high enough in energy, actually your electroweak force and strong nuclear force are the same force. So basically, what grand unified theory tell you is that what you're seeing in lower energy is a manifestation of something that is of a force that actually is the same. Is 3 different manifestations of a force that is actually the same at higher energies. So we've never detected this, and grand unified theories are a window into physics beyond the standard model. And the other thing that is important to say is that when we're talking about energy scales of grand unification, those are very high, which means that you can build TeV scale colliders, but it's very unlikely to get to the grand unification scale by smashing particles together. So you kind of need a different way into this type of physics, and looking for proton decay is one of them. Okay, so how can the proton decay, or like what are the modes that that they can decay? Well, it depends. Different theories predict different decay types. And in particular, the golden channel for argon detector is proton that decay into a kaon and kaon and neutrinos. And golden modes for Cherenkov detectors, or like water-based detectors, are the proton that decays into a E plus pi naught. Super K, which is the detector we mentioned last time, is the leader for all the modes actually, and for them, their preferred decay mode, the one that they are most sensitive to, is this second one. Again, like discovering proto decay in general would be like, well, even one event would be transformational, but depending on the type of event, you're picking which family of grand unified theory is correct. So different, like the idea is that you look for all the modes you can in your detector, and hopefully you're gonna see one. So why? Well, so first of all, what is the signature? Again, like for big liquid argon time projection chambers, the signature is the proton. It's just a kaon in the detector. Like neutrinos are, just if your proton decays into a kaon and you have a neutrino going out, you just have one neutrino, and the probability that interacts are extremely small. So in general, you have your kaon hanging in your detector, and it would kind of look like this. It would go, and then it would decay into, for example, a muon and an electron. And and this happens, like the probability of the proton decaying is extremely small. And so you really want to pick these guys out as much as possible. So the current experimental limit, so this is a decay. So the equation that regulates the decay is an exponential, right? So you talk about the half-life in terms of years when you're doing experimental limits. All these experimental limits were set by Super K, including the proton that decays into K plus nu bar, even though the kaon is under Cherenkov threshold. And I'm going to tell you, sorry, I'm just going to go, there's not a whole lot of time. So the way that a water Cherenkov sees a kaon under threshold is actually by detecting the muon and detecting the nuclear de-excitation photons that come after the nucleus is left in an excited state. So the big takeaway from this slide, although it's this axis here. So in order to, like, this process is really, really rare. So right now we've never measured one, but the time scale of the proton decay, so the half-life of the proton decay, is order of 10 to the 33 years. So like way more than the age of the universe. So how do you really look for something like this? Well, you kind of have two options. Either you look at a proton for 10 to the 35 years, which is not doable, or you look at a lot of protons all at the same time. So you look to a lot of protons for a very long time, and with as low as a background as possible. So you don't want to be fooled by something similar to your kaon hanging out in the detector if you're looking for a proton that decays into K plus nu bar. And you want to be very, very efficient. So you want to look at your bulk of protons for a very long time, and if something happens, you really want to get it. And I kind of fooled you here again, like with this simplified kaon decay mode, but actually the kaon can decay in several different ways. So it decays 63% of the time in this particular way, but it also can decay 20% of the time in pions and pi plus and pi naught. And again, if you really want a very high efficiency in finding this kaon, you kind of have to be sensitive to it in all possible topologies of its decay. Okay, so again, like the challenges here is that you need to look at your TPC or the protons in your TPC for an extremely long amount of time. And you need to look at them constantly, like, because you really don't want to blink the second that this very, very rare process happens. So in terms of readout, it means that you need to collect the data from your TPC constantly. But this is a problem for Dune, because 1 second of full stream readout for Dune, for the Dune 1.5 million wires, is 4.6 terabyte, which means that if you look, like, we're doing proton decay searches for orders of years, as you can see here in the sensitivity, which, you know, like at the first go, it seems that you're collecting like petabyte and petabyte of data. Of course, this doesn't happen. What happens is that you need to develop triggers in order to reduce the data challenge. So you need to develop stuff like some way to get rid of all the data that is not interesting and only keep events with potentially 1 KO. The background for this type of challenges are atmospheric neutrinos, mostly atmospheric neutrinos that produce you know, kaons in your detector, which hopefully you're going to be able to weed out by properties of, you know, understanding properties of the neutrinos.
So we need to hear the end of the story, Helena.
I'm here. Last 2 slides, I promise.
Because we need to leave room for Kate.
Yes, I'm coming. Okay. So so again, like, Dune will provide a lot of opportunities, both in your in terms of oscillation physics, but also in terms of non-accelerator physics. So this is what I had. Like, actually, it was really quick. The end. Again, like, we do a lot of different physics. So hopefully I gave you a taste of the LArTPC program at Fermilab to understand, you know, from hadronic interactions to rare searches to neutrino properties. Each search comes with particular challenges and hiccups, which will require ingenuity and brain power. And then it would be exciting if you could come to and help us with this. And what I left here are resources to come visit Fermilab through internships and programs. And I started at Fermilab with something like this 11 years ago. When I was a baby undergrad. And so I hope that this will be helpful for you. And so that's it.
So thank you very much, Helena. I mean, that was very interesting. Before people go for a coffee, I would ask if those that are okay can turn on their camera so that we can take a group picture with Helena. So you, Helena, okay, fine. So let's see. So in fact, a lot of people, if they want, they can ask, they can take the picture. So let's wait for a few volunteers that connect brave enough. And I don't know how to. Yeah, okay. Well, maybe some people can have some special setup in there so that they can select those that have opened their cameras, but I don't. So feel free to take pictures, and we'll do the same.
Well, it's nice to see your faces.
Right. So this is the people that have not asked questions, right?
Oh,
no, that's okay. Okay. So thank you very much to you, Elena, and to all that have opened their cameras so that we can put a picture together with a small article that's going to come out of this school in the university's annals. Okay.
Well,
so,
it was a pleasure. It was a pleasure. Please, if you have questions, send me an email or a message. I'm here.
Okay. Or if you have any questions, you can do that now. But we go into coffee break so that you're fresh for the last talk of the school. And Elena, in fact, I do have a question. So since just feel free, everybody, to do what you want. This is the break. So concerning the measurement of the properties, the cross section for pions, you didn't mention. So I guess it doesn't work. I wanted to know why. DDX as a way of particle ID. Why I would have expected that, for instance, you said we have a magnetic moment, a magnetic field, and then by measuring DDX, we get the speed, and that's our ID. Instead of use the time of flight, DDX doesn't work in this region.
Well, no, I mean, DDX where? Because I mean,
you measure DDX in the TPC, right?
Yeah, we do measure DDX in the TPC. That we can do. So there's a few caveats. So one is that we would like to know things before they get to the TPC. So